Okay, here we go. So this is going to be the MUX example that I walked you through when I introduced this, right? So I have a 2-to-1 MUX that I've built into a 4-to-1 MUX. Remember this? Okay, now I need to build a test bench. I'm going to add a source. The difference is it's going to be a simulation source, right? That's what a test bench is a simulation to make sure it works. I need to create a new file, and I'm just going to call this mux_tb. That _tb is kind of the standard notation to let you know that it's a test bench, right? We hit OK. We hit finish. I'm not going to give it any inputs. And I'm going to see it pops up now inside of simulation source. Notice that mux4 and mux_tb are all simulation sources. Mux and mux4 are both design sources as well, but they are also simulation. mux_tb is only simulation. Now there's one issue here is that right now this mux has this little icon next to it that looks like a green dot with 2 gray dots under it. It's because it thinks that mux is the top level file, which it's not, right? That's my test bench. So I right click on it and see this, it says set as top with that little icon with the green and 2 gray dots. Click that button, that test bench, once it updates, is now my new top. That is the file that it's going to try and simulate when I tell it to. So I'm going to open it up. I'm going to do the same kind of process that I do in the design files, where I'm just going to delete some of these comments to clean it up and make sure I uncomment the IEEE numeric standard. Now, a test bench doesn't care about anything in the outside world, so it doesn't need any ports. As far as this class is concerned, you will never create ports on your test benches. Okay, now we do the same kind of thing as when you create your hierarchical design, where I'm going to go to my mux4. Oh dear, it's been deleted. Well, I'm going to use the mux so that I don't have to spend a bunch of time. Okay, I'm going to go to the entity and I'm going to copy and paste it, right? That's what I told you guys to do when you're making a component declaration. My test bench needs to know that there's a component. So let's go back to the test bench. Inside architecture, before the begin, I paste the entity. I then rename, because it's not an entity. I already have an entity that's a test bench. It is now a component. I don't get to end the mux, I end the component. That's the only changes I need to do. Now the test bench is fully aware that I have a component called mux. Now I need to create an instance of it. I'm going to call this UUT, unit under test. The thing that I'm testing is a mux. That mux needs a port map. That port map is going to have an X, a Y, an S, and an F. The left side is my ports. The right side are the signals that are attached to those ports. This is exactly the same as what you've done in your 2-bit adder file, okay? Now, what plugs into X? Well, I have no ports, none at all. That means I have to create every signal that I want. So what I'm going to do is go ahead and start creating those signals. Signal. I need an X, Y, S, and F, right? Oh. Those guys need to be of a compatible type, which is this standard logic. I probably typed something wrong, right? Is it? All right, I'm being brain dead, guys. What am I missing with the signal declarations? Look at your signal declarations, guys. What do you need? What am I missing now?
That's what mine looks like. You need to do like a 1 down to 0 thingy. No, because it's just the standard. They're just standard logic, not vectors. Or
Okay.
are you gonna say in?
I don't need ins.
It's just the signal.
Is it not like the commas? No. Well, we're going to do what anybody does, and we're going to pop up and see what my brain dead mind is trying missing. We just type VHDL signal declaration. Hopefully it pops up with something useful for us. It looks like I'm right.
Yeah. Well, I was just throwing the catch.
Standard logic. Okay, signal standard logic. Error syntax near signal. Oh.
It has to be before begin.
It has to be before the begin. This is why like I should actually take the time to format my code, because otherwise you do stupid crap like that. Okay. X, Y, and realistically, I strongly recommend doing _TV at the end of all of your signals, because when we get to the actual testing, it makes a lot more sense. Now I have these signals. I can just plug them in to my ports. Oops. Notice I use a lot of copy and paste, and then I need to add the commas. Ta-da! I have made a unit under test called mux. Okay. Now, the last thing that I need to do is tell it how to use these signals. I must assign all of my inputs, and then the unit under test will assign the outputs for me. Now, what we do, we haven't talked much about this, but I write the word process begin. Anytime I write a begin, I jump down and I write the end that goes with it immediately, so I don't forget it, because you can get like massive cascades of ends and it's easy to lose them. So I said process begin, go add end process, right? Now it's as simple as writing, I want my X TB to get assigned to, right? This is just like your digital logic, some value. When we assign it to a bit value or standard logic value, we say tick, right? Similarly, my YTB is going to start at 0. And my STB will start at 0. Got it? Now, this signal XTB at the beginning of this process is going to be 0, as is YTB, STB. FTB will get assigned based on whatever the logic of the mux is doing. Right? Make sense? So I don't have to assign F. What I do then is I say, wait, let's say 10 US. Not America, it is microseconds. Oh, I need one more. Wait for 10 microseconds. Okay.
If we had a lot of these TVs, could we do like a vector so that we could write out, you know, like, and then assign X to like the first index of the vector, and then that way we can just write like take 001, take 001.
You can. Yeah. Yes. I do it this way, especially in the beginning, because it is more clear. Right. For those of you who have advanced computer science training, it's going to seem overly simplistic, but you have to remember that there are people in here that have never touched a programming language. So that's who this is designed for. Okay, so now I'm going to wait some time. And here's the great thing. You know how I like copying and pasting? You can guess what I'm going to do. Copy and paste, right? Now, if you know computer science, it's pretty obvious. I could write a for loop. and make this automated test, but I'm not going to. I'm going to brute force it. Okay. Well, now I want to change Y. I forgot one thing. I need to remember to have the wait. Because if I don't wait, it happens instantly and we don't see anything, right? Problematic. Okay. So once again, copy and paste, including the wait statement. Now, I have 0, 0, 0, 0, 1, 0. I'm going to go 0, 1, 1. Remember that the S for my mux determines whether it puts the X or Y on the output, right? So now we're going to change X. So what you should see then is in the beginning, S is 0, X is 0, so it's going to take 0. So the output FTB is 0. Down here, where XTB is 0, YTB is 1, STB is 0, still 0. But here, I've taken 1, YTB is 1, it should go to 1. Now, this is what it should do. If I find out what it does do, on the left, under simulation, I push the button, run simulation. It'll pop up and says run behavioral simulation. That's what you want. It'll ask if you want to save. You do. It'll take a little bit. Usually not this long. I may have done something weird. It is kind of an infinite loop, actually. Now, you're going to get a big window that looks like this that may or may not be helpful. In the beginning, the very first thing that you should always do, especially when you're learning, is there is this button that is 4 outward facing arrows. There are arrows pointing in the corner. If you push it, it will zoom to the full scale of your simulation. Now, remember that I told it to wait for 10 microseconds. If I look at this, my full span is 800 nanoseconds. I'm not getting even to the first change. So I can run for longer, which is actually now hidden by my drop-down menu and is not very helpful. Oh, see up here, 300 nanoseconds. I could select this, click on microseconds, and I ran it like 4 times. So I'm going to just run for another 50 microseconds. Now, there's this play button with what looks like in like italics M. And if you're far away and want to come look up, it is not an italics M. It is actually like an italics T in parentheses, which means run for some amount of time. So if I click that now, it will run for another 50 microseconds. And once again, I'm going to click this zoom fit button. And now on my test bench, I can see that I have in the beginning 0, 0, 0, 0, right? That's what I said it should be. After 10 microseconds, that's right here, it's 0, 1, 0, and my FTB, the bottom line, is still 0, which it's supposed to be, right? Because I'm taking X and putting it on F. Well, here, my select is still 1, is 1, so now I'm taking this Y, it's a 1, it puts that Y on the F, so on and so forth, right? This looks kind of familiar from the exam, right? This is exactly what the exam is doing and allowing you to visualize how your circuit is functioning. Now, in the case of yours, you need a lot more statements, right? Because you're going to test all inputs to your 2-bit adder, which you're going to add 0, 0 to 0, 0, 0, 1 to 0, 0, 1, 0 to 0, 0, and so on until you add 1, 1 to 1, 1, right? Make sense, everyone? Literally all you have to do for that is in your test bench, you would just write, because you're going to have a 2-bit vector called like X underscore TB, right? But let's pretend it's A. You write ATB is equal to, and for vectors, you use quotes, 0, 0. And then I would wait for some amount of time and then change the values, wait again, change the values, step through. Your hand in is going to be a screenshot of that waveform of you testing all of those things. Right? Make sense? Okay. Now, there is one last thing that I recommend doing is at the end of the process, right before the end of the process, you can write the word wait. Don't wait for, don't wait until, just wait. And what that'll do is stop. The reason that's useful is because right now, if you look at it, it's going to just repeat on and on forever. So if I run for another 50 microseconds and zoom to fit, it just does it over and over and over again. But now that I've added that wait, if I relaunch the simulation, it would just run once and then nothing would change again. Anyways, that is test benches. The only other thing that you need to know for test benches, and this is very important, is if on the left side, there is this button called scope. If I click that, it shows me the MUX test bench and the UUT, right? UUT is unit under test. That's what I called my MUX. If I click on UUT and click on the objects tab, this X, Y, S, and F are actually the signals that are inside of that MUX. So X underscore TB is what I see at the test bench level, whereas this X that I can drag and drop onto here is the X that is inside of the MUX. So that I can see, for one, internal signals that don't have any ports, right? This is the only way to access those. And two, I can check to make sure that I've hooked things up to the right thing. Now, sometimes if it doesn't, you'll drag and drop and it won't automatically update like this one did. All you have to do is push the top center button that is relaunch simulation. I click relaunch simulation. It'll take a little bit of time. It's going to go back and look at that test bench, and it's not going to work probably because I have that A equals TB in there, but unless I deleted it. Oh, no, I deleted it. Cool. So it ran for not 20 microseconds. So now I have to push that run for button. If I run it again for a very long time, it stays the same because I added that wait statement. It doesn't repeat that process because I added wait. That is all you need to know about test benches for now. I will save this video so you can come back and review.